So just to give a recap of what we looked at in the last session was we started with the OSPF and we looked at into its full form, its meaning of the full form. It's a layer 3 protocol. It supports classless. What is the AD value and what is a link state protocol? It also supports ECMP, etc. We looked into that perspective in the last session. Then we had a small discussion on, not a small, a big detailed discussion on why EIGRP is preferred in the enterprise side and why OSPF is preferred on the service provider side. Right. There are a lot of reasons where EIGRP is not preferred because EIGRP uses a lot of metric values in order to find the best one, whereas OSPF uses only less metric. That is the bandwidth. It uses bandwidth as the metric in order to find the shortest path. Right? And in a service provider environment, we prefer faster calculation rather than having a large calculations in order to make our decisions faster. And then we looked at a few aspects of OSPF where we can divide it into multiple regions, which is basically called as an area. And you can divide the overhead of each and every router in different areas and handle them separately. Right? And we started our discussion with single area OSPF. We did not discuss what an area is, but area is another major part in OSPF. We started our discussion with single area OSPF and that also with the network types. There are three types of network types: point-to-point, broadcast, and stub. Point-to-point is for serial, broadcast is for Ethernet links, and stub is for the loopback addresses. Right? And then we started our discussion on the configuration, right? Where we write the configurations. We understood what is the meaning of this router OSPF1, how a router ID is elected, then what is the not influence, what is the importance of this network command. And we also discussed how this network command is actually executed, or how this network command is basically working. With the network command, what is happening? The router is actually doing a dynamic discovery of its neighbors, meaning that when the OSPF discovers or whatever interface that it chooses through the through the network command, it sends out hello messages through those interfaces, as well as it tries to discover a neighbor on that interface, right? So it's doing a dynamic discovery. And we looked into the contents of the hello message, and then we started discussing the OSPF states. So there are 6 OSPF states: init state, two-way state, xstart, exchange. Then we discussed about loading, and then we came to the full state. So this is what we had discussed in our last class, right? Moving on with that discussion, today we will discuss what are link state advertisements, or basically LSAs. So first of all, let's try to understand what basically is the meaning of LSA, right? So LSA full form is link state advertisements, okay? And the meaning of link state advertisement is that any router, for example, here R1 router, right? It has different links. It has 3 links that is connected to it. One is the serial link, and 2 are these loopback interfaces, right? So it has 3 interfaces that are connected to it. So R1 is going to advertise the state of these 3 links. That is what you call as link state advertisements. Advertising the state of these links by an OSPF router is LSA. So R1 will share his LSA with R2. R2 is going to share his LSA with R1. So basically what is happening? LSA is created for each and every link. Okay, LSA is created for each and every link that is connected to a router. So what basically is happening? R1 is sharing about its own connected links and whatever links that it knows of with R2, thereby populating R2's routing table. Similarly, R2 is going to share his information about its own connected links and its own or its connected links and the links that it knows about with R1, thereby populating R1's routing table. Okay, so as I said, the main work of any IGP is to populate the routing table first, then find out how to then have the additional features of finding the best path to reach that destination. Right. So this is link state advertisements. Now there are basically 8 types, not even 8. There are 10 types of LSAs. I have mentioned only 8. Okay, and out of these, even 10 or 8 that I mentioned here, we will only come across 6 of them. Okay, so there are many LSAs starting with type 1, type 2, type 3, type 4, and each of these types have different name. Router LSA, network LSA, summary ASBR, and autonomous system external LSA, ASLSA, or and then NSSA. Okay, these are the 6 LSAs that we will always come across. The rest of the LSAs, that is, you can see here, multicast OSPF LSA. Okay, so we also have LSAs which we will be using through multicast. Okay, this LSA 224.0.0.5 is not an LSA. Okay, when we are using OSPF along with the multicast technology, there is a separate LSA for that. That is multicast LSA. All right. So 6, 8, 9, and 10. Okay, this we already know it's multicast LSA. 8, 9, 10 are called as opaque LSAs. To be very honest, even I do not know where opaque LSAs are used. Okay, and moreover, I have never come across opaque LSAs in my working experience as well. Then moving on. Okay, all right. Okay. So first LSA that we are going to look at is the type 1 LSA, or which is called as the router LSA. Now, in few interview questions, they ask what are the information present in the LSAs or the contents of the LSA. So it's important to understand or to memorize. It is basically you need to memorize. Okay, it's not something that you will always keep in head. So even me, after teaching a lot of people about these LSAs, I still do not remember the contents of the LSA. So it's always better to revise the contents of the LSA, and most of the time every LSA has the same contents. A bit of difference here and there, but otherwise most of the contents are same. So first is the type 1 LSA, or which we call it as the router LSA. Okay, now router LSA. Router LSA is a type of LSA which is generated by all the routers. Okay, it is generated by all OSPF routers. Okay, irrespective of what the OSPF router role is, it can be an ABR, it can be an ASBR, it can be a normal OSPF router, anything. All the routers in an OSPF domain generate router LSAs. That is the type 1 LSA. Okay, so let's say these two routers, okay, they are generating their router LSA or the type 1 LSA. So let's check from R1's perspective, what are the LSAs, or sorry, what is the content of the LSA? Okay, so if you just do a show IP OSPF database, right? If you just write the command show IP OSPF database, you would basically get the different types of LSAs in the network and also the router LSA. Okay, so in the router LSA, these are the contents that you will mainly find. Link ID. Link ID is basically nothing but the router ID itself. Okay, and again, that is again who is the advertising route who is the advertising router of this particular LSA. In this case, R1 is the router which is advertising. How much time has elapsed? How much time has elapsed after generating this LSA? So it goes in seconds, right? Then checksum, we'll come to that after some time. Number of links that are connected to it. Okay, so R1 already has 3 links connected to it. We already can see that. One is a serial interface, the other are 2 loopback interfaces. Okay, now, as I said, this is a serial interface, point to point. So R1 considers this serial interface as 2 links. One as the interface itself and one as the network. So the interface IP is 12.0.0.1 and the other is the network 12.0.0.0/8. Okay, so on a serial interface, if the routers are connected through a serial interface, or if the network type is point to point. Okay, as I said, if you remember in our earlier class, I had mentioned you can change the network type. Okay, even if it is a serial interface, you can change the network type to point to point. Okay, when it is a point to point network type, the router considers the interface as 2 links. One is the interface IP itself, the other link is the network. So in total, R1 will have 4 links that are connected to it. Okay, then what is the sequence number of this LSA? So age, checksum, and sequence number. When the router generates the type 1 LSA or the router LSA, it mentions the age, meaning how many seconds before was it created. Okay, and what is the sequence number of this LSA? R1 may generate many type 1 LSAs. Okay, but whichever LSA has the least sequence number, it was generated the first. The higher the sequence number, the latest the LSA is. Okay, now what is the significance of the sequence number? Why is that sequence number even there? So let's say R1 generated its first LSA. Okay, and it reached R2. So R2, when we do a show IP OSPF database on R2, we will see R2's LSA also, and we will see R1's LSA as well. Okay, with some sequence number, let's say 1. All right, now let's say there is some change in R1's LSA, meaning let's say I deleted these 2 loopbacks. When I delete these loopbacks, R1 is again going to generate an LSA. So type 1 LSA is always generated whenever there is a change on the router. If you add a link, if you delete a link, if the link fails, or if the link comes back up, every now and then for each of these conditions, the router generates a type 1 LSA. So here R1 sent the LSA. Let's assume we deleted these 2 loopbacks. So what is going to happen? R1 is again going to send an LSA with sequence number 2. Okay. Now when R2 receives the LSA with the sequence number 2, it understands that the previous LSA that it has a sequence number of 1. The new LSA has a sequence number of 2. So obviously the newer sequence number or the larger sequence number has a latest update. So it will take out the older LSA and it will keep the newer LSA with the newer sequence number. This is the importance of the sequence number. Okay, again, sequence number is again sequence number is again used for eliminating the loopbacks in an OSPF network. Okay, I will give that to you as a homework of finding out how does sequence number help in avoiding loops in an OSPF network. It's a you can take that as an interview question from my side. Now to open up the database, the actual database. So if you remember, we had learned about DBDs. Okay. So if you remember, I had mentioned during the exchange state, the two routers will share each other's DBD. So basically, this thing, is actually a DBD of R1. It is the DBD of R1, right? Which is shared to R2. R2 also shares its own DBD. Now, if I want to open the whole database, right? If I want R1's whole database, I would write the command show IP OSPF database of which LSA. As I said, there are so many LSAs from LSA 1 to 8. There are so many LSAs. Which LSAs database you want to see? So type 1 LSA is called as a router LSA, and hence we would write show IP OSPF database router. Okay, router LSA of which router? R1's router. So we will write R1's router ID. And it will show a lot of information. And this time it will show the networks, number of links connected to R1, networks running on those links, cost to reach those links, neighbors reachable over those links, and IP address of those interfaces. So these are the information that you can see in the database when you open the actual database of the router LSA. All right. Any question with router LSA?
Yeah, got it. Like yesterday I was unable to join, but I have one doubt regarding the DBD. So I think will it send any in the initial stage before exercising summary of DBD? Like will it send any OSPF route? Will it send any empty DBD packet?
Yeah, if you go back to our discussion over here, so this was our discussion where R2 is the master and R1 is the slave, right? And we had discussed that when master sends a DBD, only then the slave can respond with its own DBD. Okay. Slave will not send its own DBD itself. It needs a DBD or it needs some kind of message from the master. Then only it will share its own DBD. Okay. So R2 has 3 links, 1, 2, 3. R4 has, let's say, it has 6 links. Not so master has 3 links and slave has 6 links. Okay. So the master sent the first DBD. R1 responds with its own DBD. Second DBD responds with its own second DBD, right? Third DBD, then the slave responds with its own DBD. Now, here is the problem. Master has completely shared his own DBD. However, the slave still has some more DBDs that it needs to share. Yes. Right? So in this condition, every time the slave responds with its own DBD, it will set the more bit to 1. When this DBD is received by the master, it understands that the slave still has more DBDs to send. Okay. So even if the master has completely sent his own DBDs, and in the response, if the slave is still sending back the DBDs with M bit as 1, more bit as 1, the master will keep on sending empty DBDs. Yes. Master will send empty DBD and the slave will respond with its own DBD. Yes. And once the slave has completely shared his own DBD, he will set this more bit to 1. Sorry, 0. He will set this more bit to 0.
Okay, due to this reason only, it will send a empty DBD, right?
No. See, it is still. Yeah. The empty DBDs are only sent when slave has more DBDs to share.
More DBDs. Okay. Yes. Okay. Then, like one of the interview question at Juniper, that's why I asked you. I have not attended, but someone has. I have asked in LinkedIn, so they told me that like this they have asked. That's why. So
yeah.
Yeah, got it now. Yeah.
Okay. So this was with the router LSA. Okay. So as I said, you do not have to go much in depth about the what are the information inside. These are the basically information of the router LSA. Networks that are connected to the router, number of links that are connected to the router, networks that are running on that router, IP addresses of those router, cost to reach those routers. So if I just simply write that down, number of links that are connected to the router R1. And if you remember, I just mentioned R1 thinks the serial interface has two networks. So in total, R1 is connected to 4 networks, right? Network running on those networks, right? So 12.0.0.0/8, and it will also mention as 1.1.0.0.0/8 network. Okay. Cost to reach those links, because they are directly connected. The cost is 0, obviously. Cost is 0. Okay. Neighbor reachable over those links. Obviously, loopback, there are no neighbors, but over this serial interface, which neighbor can it reach? So it will mention R2's router ID. Okay. Then IP address of this interface over which the neighbor can be reached, 12.0.0.1/8. So these are the information that are present in the router LSA, and router LSA is created by each and every router. Similarly, R2 is also going to create its own router LSA and share with R1. So let's check R2's LSA. So he will say number of links connected to it, 4. What are the networks that are running? Again, 12/8 and 1/8 network, right? Not 1/8, sorry, 2/8. This is 2 loop back. Cost to reach these networks, obviously, these are directly connected. So 0.
0.
Neighbor reachable over that interface, that is R1's router ID, and the IP address of that link, 12.0.0.2/8. Okay, these are the information that it will share with R in the router LSA. Clear? Any question?
Yes. No. I don't have. Like,
okay.
Any questions regarding like interview questions on this router LSA? I think.
Yeah, I mean, basically, yeah, I mean, what are the, see, when it is LSA, okay, either they'll ask you there are two types of questions. First, what are the contents of the LSAs?
Okay.
What are the contents of the LSA? As I said, most of the time, these are the contents that you will always see in most of the LSAs. Okay, number of links, network running, cost to reach those links, neighbor reachable, IP addresses. It's okay. Okay. And most of the time they'll ask only the contents of the router LSA, and they will not even specify. They'll just say what are the contents or what information is shared in LSA. That's all. So they're not going to ask what is the information shared in LSA 3, what is the information shared in LSA 4 or LSA 5. No. Even if they ask, anyway, we are going to go through that. You can just mention that. But it's always better to know this part.
Yeah.
That's all. Okay. Third type of question is what they'll ask is scenario based questions, where they'll ask what kind of LSA will be generated in this situation. How many LSAs and what are the different types of LSA that will be generated in this situation. So we'll discuss all that in today's class. Don't worry.
Okay.
Okay. Now moving to the type 2 LSA, which is also called as the network LSA. Now the problem with type 1 LSA, there's no problem with type 1 LSA. Okay. The problem with point to point, if there are, not point to point, when the two routers are connected with Ethernet link, or they are connected in a broadcast environment. So if you remember, we just spoke about 3 types of network types: point to point, broadcast, and stub, right? We just went through the point to point. Now, in a broadcast environment, Okay, as I said, OSPF thinks an Ethernet interface as broadcast. Why? Because from OSPF's perspective, Ethernet link means that it is connected to a LAN network. When it is connected to a LAN network, obviously to that interface, there may be multiple other routers which are connected. And if multiple other routers are connected in the same LAN segment, then that is a broadcast segment. And that is how OSPF thinks Ethernet links as broadcast. Now, imagine this scenario. There are 5 routers. Okay. R1 over here. Okay. When R1 wants to imagine this scenario, R1 is trying to create OSPF neighborship. So R1 has to create OSPF neighborship with R2, R3, R4, and R5. Okay. So one router is creating OSPF neighborship with 4 other routers. We have 5 routers. 5 routers will create 4 adjacencies. Okay. So in total, between these 5 routers, you have 20 adjacencies. You have 20 adjacencies that are created, right? And again, it's a kind of a problem. How? 20 adjacencies is not a problem. Problem is when R1 wants to share some information, right? When R1 wants to share some information, it is going to share with every router. Okay, four routers. Now, when these 4 routers will receive R1's LSA, they will share it with their adjacencies. Okay, so 4 into 20 adjacencies. You have 20 adjacencies created. You have 80 LSAs flooding. You have 80 number of LSAs. Just that is the single LSA. That's only one single LSA. Right? It will be flood across these 5 routers. So what is happening? Okay, all those LSAs are identical. There is no single change. All those LSAs are identical. So the problem is with such kind of scenario, which in a broadcast environment where OSPF thinks Ethernet link as broadcast environment, flooding of LSAs is a big problem. Okay, then when flooding of LSAs happen, your router's database will keep on changing. Okay, your database need to be updated when one LSA is received. And if you remember, sequence numbers matters a lot, right? Sequence numbers, the age, everything matters a lot, right? So every time a new the LSA is received, the database will change. When the database change, your database is unstable. We do not want that, right? So for such a scenario, we came up with the network engineers, they thought this perspective from a classroom analogy. Okay, from a classroom analogy. So this guy is the monitor, class monitor, okay, or class representative. Okay, he is the monitor, right? Now we know that whenever the teacher wants to share some information with all the students in the class, okay, first thing, let's assume that she's not there in the class. So she calls the monitor and she shares that information with the monitor in the staff room, right? Then what happens? This monitor is going to share the information with all the kids, right? This is what basically happens with the class monitor. All the information that the teacher shares with the monitor is supposed to share it with the whole class. Now, if the monitor is absent on some day, there is an assistant monitor, right? There is an assistant monitor who takes over the role of the monitor. Then the teacher shares the information with the assistant monitor. The assistant monitor will share the information with the whole class, right? So using the same analogy, the OSPF engineers, they came up with a concept of DR and BDR, which basically is your designated router and backup designated router. So your designated router is the monitor of the class, and your backup designated router is the assistant monitor of the class. Okay. Now with this monitor and the assistant monitor, how is the broadcast issues solved? Let's look into that part. Okay. Now, what happens is that in such a broadcast environment, as we know, there are problems. The problem is with the flooding of LSAs and the instability of the database. So for such a scenario, what we do, we elect the DR or we elect the monitor. Obviously, in class also, we elect the monitor, right? Or the class teacher elects the monitor based on some criteria, right? He is good with leadership. In our times, okay, I'm not sure how old you are, Srinivas, but I'm pretty sure we both are of the same age, almost the same age. Our class teacher used to elect the class monitor based on the topper. If he is top of the class, he is the class monitor. The second rank guy would become the assistant monitor, like that. Similarly, so similarly in our environment over here, whichever router has a highest router ID becomes the DR or the monitor. So in this scenario, you can see here, these are the loopback addresses, and we know that the router ID is chosen first based on the loopback address, and if the loopback address is not present, then it is chosen based on the physical IP address. Correct?
Yes. Yes. Hello?
Yeah. Give me a minute.
Okay.
So the election is first done based on the priority. Okay, OSPF has a default priority of 1. So obviously between these 5 routers, the priority is going to be equal, right? It is going to be equal. So this is not a optimal way to find the optimal way to find the DR. The next tiebreaker is the highest router ID. Whichever router has the highest router ID becomes the DR. Now router ID, we know that is elected based on 2 things: highest loopback or the highest physical interface. And since here all these routers have loopback addresses and R5 has the highest loopback address, this router becomes the DR. Okay. Then whichever router has the second highest router ID becomes the BDR. So router 4 becomes the BDR. Okay. This process we already know, right? Whenever someone asks which router becomes the DR, which router becomes the BDR, so we immediately say, okay, we immediately say the first, we immediately say the router which has the highest router ID becomes the DR. Okay. This is a theoretical process, but actually what happens is that the router with the highest router ID first becomes the BDR. So let's assume, okay, now you're confused. Okay, how is that possible? So first, what actually happens is that let's assume that we switched on or powered on these routers at single, we powered on these routers at once. Okay, at once. So what actually happens is that these guys, okay, because we powered all of them at once, just like your spanning tree protocol, every switch considers itself as the root switch. Similarly, all the routers over here will consider themselves as DR. I am the DR. I am the DR. This guy will also say I am the DR. All the routers will say DR. Okay. They will share the information that I am the DR. This is my loopback address. This is my interface IP, everything. And this information is shared with everyone. But with the DR, they also need to share the information of BDR, which none of these guys will say who the BDR is, because they don't know who the BDR is, because BDR is not yet elected. Everyone is calling themselves as DR, right? So BDR is not elected. So after some fraction of second, all of them will realize there is no BDR. So someone first has to become a BDR. Okay, so again, the highest router ID will become the BDR. BDR. Then the BDR will start looking for DR. Who is the DR? When there is no DR found, R5 will then become the DR. Then again, once the DR has been elected, again a BDR election takes place. Clear? This is actually how the DR BDR election happens. First, it's always the BDR that is elected because all the routers consider themselves as DR. So there is an election for BDR. Because all the routers are considering themselves a DR, there is no BDR. So eventually they fall back to electing the BDR first. So in that process, R5, because it has the highest router ID, it becomes the BDR. Then these routers will again look for DR. There is no DR. When there is no DR, this guy will automatically take over the role of DR. Then once the DR is found, these guys will elect for BDR. And the other routers, which are not a DR, not a BDR, they are called as DR other routers. Clear? Any question?
Oh, got it, but little bit confused. BDR
It's
first.
all, yeah, it's always the BDR first. Just remember, it is always the, like, for example,
While they're sending in the first like where they're powered on at once all the routers, so they will send. I think in the BDR place, DR place, I think both same information will be there. I think while they're sending.
yes, you can think that DR and BDR. No. If the same router cannot be DR and BDR, either it can be DR or it can be a BDR. Okay, so when it's not in this scenario, we just assumed that all the routers are powering on at the same time. Let's imagine that this is DR, this is BDR, and this router is not there in the network for now. We powered on this router first. We powered on this router. So when he sends, or when he is powered on, when he sends the LSA, right, he will call himself as DR. It will go to everyone. But then this DR will send back information, dude, I'm already there.
Okay. Yes. Correct.
So DR now will have the information of DR as well as BDR, both. This guy has the information of DR and BDR. This guy also has the information of DR and BDR. So they both will say that we already are there in the network who are representing as DR and BDR. So you cannot be the DR. So R2 eventually fall backs to becoming DR other. Okay.
When they initially they are sending, they send only LSA one only, right? Until unless they select DR, because it will be.
Now, okay, I did not. Yeah, okay, I did not come to that part.
Okay. Yes. Okay.
Where is the LSA2 coming in this part? You got the point. Where is the LSA2 coming in this part? LSA2 is generated only by the DR. LSA2 saying that I am the DR. Okay, now we'll sideline this for now. Let's sideline this for now. This guy has become DR. This guy has become BDR. So now what is going to happen? All the routers, all the other routers are going to share their database only with the DR and the BDR. Okay. So now what is happening here is that there are 5 routers. Okay. There are 5 routers and they are sharing their information only with 2 routers, or they're sharing their database, or they're forming adjacencies only with 2 routers. Okay. Yeah. So 5 is obviously 5 will R2, R3, and R1. Okay, they will form adjacency with DR and BDR only, not between each other. Okay, DR and BDR will form adjacency with all routers. Okay, so with only 5 routers, it does not seem to be a big difference. Okay, adjacency does not seem to be a big difference. Okay, however, when you have hundreds of routers in the network, this seems to be a big difference. Okay, with 100 routers, it's a huge difference. 100, imagine there are 100 routers which have to which have to have an adjacency with 99 other routers. So you have 9900 adjacencies. But with such scenario, with the DR and BDR kind of thing, this seems to come down significantly, provided all of them are in the same broadcast segment. Okay, which is very hypothetical. That's a different thing. But imagine 100 routers connected through a switch. Imagine the level, the amount of adjacencies that will come down from 9900. Okay, so as I said, with 5 routers, it does not seem to be a big difference, but with a huge network, it's a lot. Anyway, as I said, the DR other routers will form adjacencies with DR and BDR. The DR and BDR routers will form adjacencies with all the routers. Okay, irrespective of their role. Now, when DR fails, let's say R5 failed, for some reason R5 failed, or the link between R5, the link of R5 failed. So what will happen is that after the hello timer is expired, we know that hello timer is sent at every 10 seconds of interval, and dead timer is 40 seconds, right? So after 40 seconds, when the BDR does not receive hello from the DR, it will take over the role of DR. It will take over the role of DR, and then again the BDR election takes place where R3 will become the BDR. Now, the thing that we sideline. Now, what is going to happen? Till now, everyone had formed adjacencies with the DR, where DR had said, "I am the DR. You share the information with me. You share your database with me. Okay, you share your database with me, right?" Then, the moment R4 changes to DR, it will send an LSA 2 saying that now I have become the DR. Now all the other routers, you share with me, you share your adjacencies with me. Now, after R4 has become the DR, R3 or whichever router has the higher router ID will become the DR. So other routers will also share their database with the BDM. So LSA2 is generated only by the DR when it becomes the DR, not any other time. Okay, that's the only time when your LSA2 is generated. It is created by the DR to tell other routers in the same network that I have become the DR, share your database with me and form adjacency with me. Clear?
Yeah, yes, got it.
Hmm.
Every time it is this LSA port is creating confusion for me.
It's very easy. It's very easy to understand. Once you get the meaning behind them,
Like,
why so, it's
mm.
very easy. I hope till now there is no problem.
Ah, yes, yes. Because they mostly the interviewer also they confuse on this spot only.
Yeah,
Mm.
correct. Okay, so now before we jump into the next LSA 3, let's talk about area, which I have not spoken till now. So area is a huge concept in OSPF. But why did we come up with the uh, uh, why did we come up with the feature of area? So imagine this as one huge network. Okay, imagine this thing as a huge network. Now the problem with one single OSPF area. Let's say the link between R5 and R6 fails. Okay. Now we know that R5 and R6 will generate the LSA number one, because we just learned any change in the network, any change in the link, the router is going to generate the LSA number one. This is what we had discussed, right? So R5, the link between R5 and R6 fails. R5 is going to generate LSA number one. It's going to LSA, LSA, LSA. R6 is also going to generate LSA. Now, this LSA is going to propagate in the whole network, right? So eventually R12 is going to forward to every router. All the other router are going to forward to every other router in the network. Now imagine the overload on R1. It is going to receive LSA from so many other routers, not just R5 and R6. Every other router is going to send the LSA to R1. Imagine the amount of load that is happening on R1. Okay. Then let's say R1 received it. Okay. Obviously, R1 needs to respond to that LSA, because R5 is sending LSA saying that the link between R5 and R6 has failed. And it is also looking for an alternate path. Okay, so it's an LSA link state advertisement, for which link state update. It will send a link state update. Okay, R1 needs to send a link state acknowledgement. This is not advertisement, but this is an acknowledgement. Acknowledgement to all the LSAs that it receives. Now that LSA is going to be sent across all the devices from all the network. Again, R5 and R6 will have a lot of LSA being received. Okay, so first problem, LSA flooding. Okay, now the second problem is that when R5 and R6, the link between R5 and R6 fail, basically they are going to find out an alternate path to reach each other. Obviously, this is the alternate path, correct? Now, the LSA or the LSU that they generated, by the time it reaches R1, they have already found an alternate path. They have already found an alternate path before this LSA reaches R1. So what is happening? The not LSA, LSU that is received by R1 is basically useless. It was useless. Correct. And the link state acknowledgement that R1 sends is also useless, because R5 and R6 have already found an alternate path. So what is happening because of that link state update and link state acknowledgement, right? Your convergence between R5 and R6 has already happened, and R1 is already being bothered for no reason. So there is a problem here. Link state, your LSAs are being flooded. Because LSAs are being flooded, what happens? Your database on every router keeps changing. Because LSAs are being flooded, each and every LSAs need to be processed. When each and every LSA and link state updates need to be processed, your CPU increases. Right. So with convergence happening at one end of the network, your every router in the network has a problem. To solve this issue, we came up with area. Now with area, what is happening? Let's try to understand. So if the link between R5 and R6 fails, R5 is going to send LSU, LSU, R6 is going to send LSU, LSU, LSU. Now, the good thing with area is that this LSU is limited only to its own area. Any LSU that is generated inside an area can only circulate in its own area. It cannot go to other area. So here what is happening? R1 is completely unbothered about what is happening in other area. So because the LSAs cannot travel from one area to another area, your LSA flooding is reduced. Let me use a different color. Your LSA flooding is reduced. Edge routers, the routers in the end of the network, are completely unbothered, right? They are not at all affected. Your database is stable because there is no more LSA flooding. Because there is no more LSA flooding, the CPU processing of each and every router reduces. Got it? This is the reason why we brought area into OSP.
Yes,
Clear?
yes, understood. Yes, clear. I think every time if there is any like any any link fails or something in case of DR also, it will send only update, right? Link state update only, no? Link state update
Yeah.
to the, all the
Link
routers,
state.
like this
Yes.
link is
Link
failed.
state updates. Yes.
Hello?
Yeah, yeah. Link state update only. Yes.
Okay.
Now, before we move into further discussion on areas, let's discuss what actually is an area now. So there are there are two types of areas. One is a backbone area. The other is a non-backbone area. Very simple. Backbone area and non-backbone area. So backbone area, okay, you can write area numbers. Okay, you can write area numbers starting from 1 up till many. I don't even know the number. Okay, you can write any number of area. Okay, so you can make
I have not remembered, but
yeah. Tell me.
655.
No. Say not 65535. No. This is not the number. It's even
Maybe
greater than
655
this. It is even
greater
greater
than.
than this. Yes, yes. So you can write write areas. If you remember, we were writing IP OSPF. Sorry, not IP OSPF. Router OSPF 1, then network command, then area. Right? We wrote area. So this area number you can write from 0 up till there's a huge number. You can write any number. You can choose any number. But for a backbone area, it is recommended that you use 0 as the backbone area. You use 0 as the backbone area. Okay. Now you can see here area 1 and area 2 are here. These two areas are called as non-backbone area because they are not area 0. Now, some interviewers, they are very, what do you say, smart ass, I would say. And they would say, why is area 0 called as the backbone area? And why is any other area 1, 2, or area 100 not called as backbone area? Okay. Very stupid question. Very honestly answering, that is how OSPF has been designed. In
Yes.
OSPF, area 0 is called as backbone area. That's it. There is no other reason. Why area 1 cannot be called backbone area? You cannot call it because that is how it has been designed. Okay, that's the brutal and honest answer.
Yes, I have studied somewhere also, like if they have not designed area 0 as a backbone now. So everyone they in the production na, they will select their own backbone area na. So it will create unnecessary problems, right?
Good answer. I did not. I never thought of this.
So yeah.
I never. Very good answer. I didn't. I never thought of this. So you are right, because OSPF is open standard, and every other vendors can use OSPF in with their routers. And as you just said, because OSPF is open standard and every other vendor can work with it, and they need interoperability. If area 0 is not considered as a backbone area, one vendor will consider area 100 as its own backbone area, the other vendor will consider area 0 as its own backbone area. Then there is a problem, right? So OSPF is open standard, and you need to have some standard process, best practice in order to create or in order to work with OSPF, and that is why area 0 is considered as backbone. All right. I don't know why they chose area 0. They could have chosen area 10 also, but I don't know why they chose area 0. There's no answer for that question. Why area 0?
Okay, but it started with 0 na. Initial the I think. Yeah.
Exactly. We don't know how. Why did they choose? Okay, your answer is absolutely right in that perspective, where we need some standard of working with OSPF. Every other vendors cannot choose their own backbone number, right? So they chose area 0. But why area 0? There is no specific answer to it.
Yes.
Okay. All right. Then there are different types of routers based on the area that they belong to. Okay. So the routers inside a backbone area, okay, the routers inside a backbone area, or the routers whose links or interfaces are inside a backbone area are called as backbone routers. So R1, R2, R3, and R4, they are called as backbone routers. All right. Then the routers that are that are between two areas, meaning that R3 here and R4 here, right? One interface of R3 is part of backbone area, one interface is part of a non-backbone area, and hence this router is called as ABR, or area border router. Similarly, R4's one interface is part of backbone area, the other interface is part of area number 1, or a non-backbone area, and hence this router is called as ABR, area border router. Okay, because it is a border, it is in the boundary or border of two areas. That's why it's called as area border router. Now, for a router to become an ABR, the condition is that at least one interface should be part of area 0, and other interface, any other interface, should be part of a non-area 0. Then only it can become an ABR. This is the condition. Okay. Again, the condition is one interface of the router should be part of the backbone area like this, and at least one interface or at least one interface should be part of a non-backbone area. Then only it can be an ABR. This is from Cisco and a point of view. Okay. Recently, I came to know that in Juniper, this is not the case. So if you're giving Juniper's interview, this is just for an information. In Juniper, an ABR, a router can become an ABR even if it is not part of a backbone area. So let's say that this interface, okay, over here, right? This interface of the router, router R11, it's part of area 3. Even this router then is called as the ABR in Juniper. I'm not sure of any other vendor, but in Juniper, if the router is part of if the router interface is part of two different area, it's called an ABR, irrespective of the backbone area or not. But in Cisco, one interface should be a part of backbone area, then only it can be called as an ABR. Okay. Now, OSPF, when we are working with multiple areas in OSPF, okay, OSPF's behavior basically changes. This is a very important question. Okay. They ask, is OSPF a link state protocol or a distance vector protocol? Okay, listen to this question very carefully. They ask, is OSPF a link state protocol or a distance vector protocol? Now we know that from our earlier discussion, OSPF is basically a link state protocol. That is its core behavior. However, when we are dealing with multiple areas, OSPF tends to behave like a distance vector protocol. So it is both. If we are dealing with OSPF in a single area, it is called as a link state protocol. But if we are dealing with multiple areas, it behaves as a distance vector protocol. Now you may ask how? So, as I said, the LSAs that are generated inside an area cannot go to any other area, right? Similarly, the LSAs that are generated in a backbone area cannot go to area number 1 or area number 2. Similarly, the LSA cannot go to area number 0 from area number 1, right? So now the problem is, inside the same area, all the routers will know about each other's links and their states. That is what link state advertisement is doing. Okay, so R9, R7, and R5, they all will generate LSA number 1. Even R3 will generate LSA number 1 through this interface. So all of them will come to know about each other's link and their states, how to reach them, what is the cost, everything they will come to know. Correct. Similarly, in the backbone area, R1, R2, R3, and R4, they will know how to reach each other. The same goes for area number 1. But let's consider this situation where R7 wants to reach R8. Where R7 wants to reach R8, how will it reach? Because the LSAs that is generated by R8, let's say R8 generated LSA number 1, it will be shared with all the routers. However, R4 is not going to forward that LSA to area 0, right? If it does not share that LSA to area 0, obviously R3 is not going to receive it. When R3 is not going to receive it, R7 will not receive it. And hence, inter-area communication cannot happen in OSPF. Correct? So for this purpose only, let's say when R8 generated the LSA, it eventually reached R4. Correct? Now what R4 is going to do is that R4 will convert this LSA number 1 to LSA number 3. Okay, where okay, so here R8 generated the LSA number 1. It went to R4. R4 converted that LSA number 1 to LSA number 3. Now, what is the information present in LSA number 3? What kind of information is R4 going to share with the routers in area 0? So let's say R8's IP address. So what? So it is sharing the LSA about R8, right? So R8's network, let's assume it is 8.8.8.8. What is the subnet mask? /32, for example, right? Who is advertising this LSA number 3? Who is advertising this LSA number 3? It is R4 or R4's router ID, right? Cost of the advertising router to reach that network. what is R4's cost to reach R8? What is R4's cost to reach R8? It will also share that. Got it? Now let's assume R4's cost to reach R8. Let's assume all the cost is 1. All the interface cost is 1. So 1 plus 1. So R4's cost to reach R8 is 2. Correct? So here R4 is going to say to reach this network, I am the advertising router and my cost to reach this network is 2. It will share this information as LSA 8 in area 0. So all the routers R2, R1, R3 will receive this LSA number 3. Now, R3 has received that LSA number 3, correct? Now, LSA number 3 was generated in area 0. So it cannot cross to area number 2 also. So R3, what it will do, it will also generate its own LSA number 3, saying that to reach 8.8.8.8, whose subnet mask is 32, and who is advertising about this LSA? Who is the advertising router of this LSA? This time it is R3. What is R3's cost to reach this network? R3's cost to reach this network is its cost to reach R4 plus R4's cost to reach R8. So R3's cost to reach R4 is, we know that we just assume the interface cost to be 1, 1, 1, 1. So in total 3. R4's cost is already 2, which is here, right? So it says my cost is 2. 2 plus 3 over here, that is 5. So R3's cost to reach 8 network in total is 5. This information it shares with all the routers in the network. R7 receives it. Now R7 knows to reach 8.8.8.8, it needs to go to R3. What is R7's cost to reach R3? That is 2. So in total, R7's cost to reach 8 network is 2 plus 5, giving us 7. So now R7 knows how to reach R8. Okay, to reach R8, the cost is 7, right? But to reach R8, first it needs to go to R3 because it is their advertising router. Now, when R3 receives it, it will say to reach R8, it needs to go to the advertising router of LSA3, that is R4. Now, R4 will say it already knows how to reach R8 because they are in the same area. So it will forward the data to R8. The same goes in the opposite direction as well. R8 will also, to reach R7, it will also consider these LSA in a similar manner. So R7's LSA, R3 will convert it into LSA3. It will forward it to R4. R4 will forward that LSA3 to R8. And to that, R8 will now know how to reach R7. Clear? This is how inter-area communication is happening. Clear? Okay, I take that as a yes. Now, when a particular router becomes an ABR, as I said, to become an ABR, the condition is one interface, at least one interface should be part of area 0. The other interface should be part of non-0, right? So here, R3, the moment it becomes an ABR, it will generate an LSA3. It will generate an LSA3 with, not LSA3, sorry, LSA1. I'm sorry. It generates LSA1, saying that I have become the ABR. How does it say that I have become the ABR? In this LSA1, it will set the B bit, which is the boundary bit. Boundary bit, which means that all these routers in area 2 will come to know that R3 has now become the ABR. Now, to reach any external network, these routers need to go to the ABR, that is R3. Similarly, R4, the moment we connect R4 to area 0 and any other area, R4 will generate an LSA 1 with the B bit. Now you may think, when does LSA 3 when is LSA 3 generated? LSA 3 is only generated when the database is being exchanged. R7's database is exchanged to R3. Now R3 needs to exchange this database with R4. It will send this database as LSA3. It goes to R4. R4 forwards this LSA3 to R8. So now when we do show IP OSPF database on R8 or R7, right, on R8, we will see summary LSA. That is the type 3 LSA, summary LSA. Under summary LSA, we will see 7777. We will see the information of all these routers. Okay, we will see the information of R1, R2, R3, R5, R7, and R9 in summary LSA, under LSA number 3. Similarly, for R7, we will see all the other routers in other areas under summary LSA. Clear? Any question? Guys, can you hear me? Hello?
Yes, yes.
Okay. Yeah, Krishna Kumar, any question?
Actually, I'm trying to listen what is going on. Actually, before that, I had not joined the call. That's why I'm not able to understand much.
Yeah, no problem. Okay. Sorry about this mess. So here, okay, the next LSA number, LSA number 5. Okay. So imagine that this is an OSPF network, and this is an EIGRP network. Okay. Now for R2, okay, for R2, it is part of an OSPF network and it is also part of an EIGRP network. Okay, or consider from R2's perspective, the OSPF network and EIGRP network are autonomous networks, meaning they are individual networks. They have their own authority or they have their own administration, right? So these networks are completely different and individual networks, right? So OSPF considers these networks as autonomous. Now, R2 over here is connected to two autonomous networks. That is why R2 is called as ASBR, Autonomous System Boundary Router. Simple, Autonomous System Boundary Router. You can see here, Autonomous System Boundary Router, right? Now, when R2 has to share the information about EIGRP network, okay, when R2 has to share the information about EIGRP network to OSPF network, what we basically do, we redistribute it. Right? When you redistribute this network into OSPF, right, what happens is that R2 will generate, okay, R2 will generate an LSA number 1, saying that it has become the ASBR. Please remember, this happens only when you redistribute. When you redistribute. Just like your ABR, the condition was one interface should be part of area 0, the other interface should be a part of any other area. Then only LSA3 is generated. Similarly here, if you just connect R2 to EIGRP and OSPF, it is not going to become an ASBR. Until and unless you redistribute it, you redistribute the EIGRP network into OSPF, then only it becomes an ASBR. And how does it tell everyone that it has become an ASBR? By generating an LSA number 1. And in that LSA number 1, it will set the E bit. E bit is external boundary bit. External boundary bit. Just like ABR was B bit, boundary bit, here E bit, external boundary bit. To tell everyone that it has become an ASBR. And if any router, they want to use the EIGRP network, they have to come to the ASBR. Okay. Then, what are the contents of LSA type 5? They may ask you this question. Okay, not contents. Basically, as I said, in general, they ask, what are the contents of LSA? So, the contents of LSA number 1 that I had mentioned, remember that and just like say that same content. It's okay. Now, for our understanding, what are the contents of LSA type 5? Okay. Network ID. Here, when R2 is advertising EIGRP network into the OSPF network, it will advertise about 23 network, right? The subnet ID. Okay. What is R2's cost? What is R2's cost to reach this EIGRP network? By default, to reach any external network via your ASBR, the cost is 20 by default. This is the default value. Okay. Who is the advertising router of this LSA number 5? It is R2. Right. And what kind of route type is it? We'll talk about route type a bit later. Okay, a bit later. This is an E2, this is an E1 route. We'll talk about this route type in just a while. Okay, probably in the next 15 to 20 minutes. We'll talk about it. So you can see here, I mentioned these are the contents of your LSA number 5. So LSA 5 is generated by ASBR. ASBR is the router which connects two different autonomous systems. And the ASBR becomes an ASBR only when it redistributes any other network into OSPF. Then only it becomes an ASBR. And how does it tell everyone that it has become an ASBR? By generating an LSA number 1 with an E bit, external boundary bit. Okay. Next. Now, please remember that LSA number 5. Okay, LSA number 5 does not belong to any area. It does not belong to any area. So let's say that this is area 0 and here you have R1, R4, here you have R5, etc. Like this. This is area number 1. Now, in this scenario, you can see R3 is the ASBR because it is connected to EIGRP, right? So R3 is going to generate LSA number 5 about the EIGRP network. It will be sent to R2. R2 will forward, it will be sent to R1. R1 is not going to convert like in LSA, like in area border router, which was converting an LSA number 1 to LSA number 3. Here, the R1 is not going to convert it into LSA number. It is not going to convert it into any other LSA. It's only going to forward the same LSA number 5 to R4 and R5. Clear? Why? The reason is this LSA is talking about EIGRP network, which basically does not belong into this OSPF network. And hence that LSA also does not belong to any area. Okay, that is why it is propagated to all the area. Unlike your LSA number 1, 2, or 3, which is generated only in a same area and it is propagated only inside the same area. LSA number 5 can move across your OSPF network. All right. Now, how does this calculation happens? How does the calculation of the metric calculation of EIGRP happen? Let's try to understand. So R3 is going to talk about EIGRP network and generate an LSA number 5. It will be forwarded to R2. It will be forwarded to R1. Okay. Now we know that in LSA number 5, the cost by default is 20. So R1 knows how to reach EIGRP network through the ASBR, and the ASBR's cost is 20. Now, what is R1's total cost to reach the EIGRP network? Its total cost to reach EIGRP network is from R1 to R3. Then R3's cost to reach the EIGRP network. R3's cost to reach the EIGRP network is 20. R1's cost to reach R3 is 1. So 20 plus 1, 21. This is R1's total cost to reach the EIGRP network, 21. Similarly, the cost of R2 to reach EIGRP network is 21. The same way, how ABR calculates their cost to, not ABR, yeah, how other routers through ABR calculate their cost to reach routers in other area is the same way how routers calculate with LSA number 5. Any question till here? Okay. Now, here, R2 is the ASBR. R2 is the ASBR. R1 is the ABR here because it is connected to multiple areas, area 0 and area 1. Now, R2 is going to create an LSA number 5, right? It will talk about EIGRP network. Now, this LSA 5, as I said, it will be sent to all the routers. R1, as I said, it is not going to create any other, it's not going to convert this LSA 5. It is going to forward it to the other routers in the network. Now, R4 here, R4 knows. Okay, R4 knows about LSA 5. So it knows to reach the EIGRP network. It knows to reach the EIGRP network via the ASBR. Okay, R4 knows to reach the EIGRP network via the ASBR. But the ASBR, when LSA 5, right? It knows how to reach the ASBR. Let me rephrase. Sorry. R4 knows how to reach the EIGRP through ASBR. But R4 does not know how to reach the ASBR. It knows how to reach EIGRP network through the ASBR because LSA 5 was generated. It now knows about the EIGRP network through LSA 5. And to reach that EIGRP network, it needs to send the data to ASBR. But how do I reach the ASBR? How do I reach the ASBR? Okay. So when R2 generated the ASBR, it would have generated with a router ID of 2.2.2.2. And in R4's database, 2.2.2.2 does not belong in the same area. correct? 2.2.2.2 does not belong in the same area, and hence R4 does not know how to reach the ASBR. Correct? Is everyone clear till this point?
I think last point I have a little bit confused, like how that ABR can send it, right? Like if
Yeah.
it doesn't know.
Come to a point. Yeah, we'll come to that. Okay. So R4 here does not know how to reach ASBR. So when R1 is forwarding this LSA number 5, when R1 is forwarding LSA number 5, it will also create another LSA which says LSA number 4, which tells these routers how to reach the ASBR. So when LSA 4 is received by R4, R4 now knows to reach the ASBR, it needs to send the data to its own ABR. Okay, it needs to send the data to its own ABR. So R4 will send the data to ABR, ABR will send it to ASBR. So here, this is the only case when your ABR will generate. It's not converting. Please do not confuse. It's not converting the LSA 5 to LSA 4. No, it is forwarding the LSA 5. It is creating or it is generating a new LSA 4, which tells these routers how to reach the ASBR via your ABR. Clear? This is when your LSA 4 is generated. So if you think, this may be an interview question. How many LSAs does an ABR generate? How many LSAs does an ABR generate? ABR, it can generate LSA number 1 because LSA number 1, LSA number 2. It can also generate LSA number 2 if it is a part of a Ethernet link. Correct? It generates LSA 3. We know that multiple areas. It generates LSA number 4. It generates LSA number 4. Can it generate LSA number 5? Can it generate LSA number 5?
No.
Now this is a scenario question. Here is an EAGR. How many LSAs will R1 generate into the OSPF network? R1 will generate LSA number 1. We know that, right? It will generate LSA number 2 because this is a broadcast network. It's an Ethernet link. It will generate LSA 3 because it's a border router for, this is area 0, area 1. Will it generate LSA number 4? We don't know. Will it generate LSA number 5? Yes, because it's an ABR as well as an ASBR. And hence it will generate LSA number 5. But in this scenario, it's not going to generate LSA number 4 because there's no need. Because these two routers are directly connected or are part of the same area. When your ASBR is not part of the same area, that's when your ABR generates an LSA number 4. So in this situation, R1 generated an LSA number 4 because it knew the two routers, R4 and ASBR, are not directly connected and they are part of two different areas. And hence, it had to generate an LSA number 4. But in this case, there was no need of LSA number because the two routers are directly connected to the ASBR. Clear? This is again a situational interview question. How many LSAs will R1 generate? Clear? Any question with this?
No.
Now, Again, a situational question. Which R4 is the ASBR, R2 and R3 are the ABRs, R1. Which ABR will it choose to send the data to ASBR? Which ABR will it choose to send the data to ASBR?
I think it will do some load balancing.
Look at the diagram carefully.
Okay. Based on the cost, here different
Correct.
links are there.
Correct. So this cost is 64. This is 1. This is 1. This is 1. So for R1, from here the cost is 64 plus 20, whatever the network here is. From here, it's only 20 plus 2. So it will choose this ABR to reach the ASBR. Okay. Now, next situational question. What if this is also the Ethernet link? Now, how will it choose?
In this case, it will do equal cost load balancing.
Okay, it supports equal cost load balancing. Yes, it may do ccnp. However, there is a catch. So again, this question was asked to me in Amazon. Okay, and yeah, I think only in Amazon. Yeah, but I knew the answer. That's a different thing. So this is ASBR. You have R2 and R3 acting as ABR, and you have R1 there. The thing is, it's not about choosing. It is about who is going to, which ABR is going to send the data towards R. Okay. Give me. Now, what is going to happen here is that LSA 5 will be generated. Okay. LSA 5 will be generated. It will be sent to R2. It will be sent to R3. Now, the problem is if R2 shares it with R1, R1 will share with here R3 is going to share that with R1, and this LSA will go to R2, and R2's LSA is going to R3. So what is happening here? There is already a loop. You got my point? There is a loop here. How is the loop forming? R4 shares his LSA to R2. R2 shares his LSA to R1. R1 is, this is LSA number 5 we are talking about. LSA number 5 does not belong to any area. Remember that. R1 will share that to R3. R3 is going to share that back to ASBR. Loop. Similarly, in the opposite direction, R from R3 to R1, R1 to R2, R2 to R4. Again a loop. Okay. So in this situation, what is going to happen is, first of all, when R2 and R3, because they are part of the same area, okay, because they are part of the same area, they will generate LSAs. He will generate LSA number 1. It will come to R3. R3 is going to generate LSA number 1. It will come to R2. So now R2 and R3, they both know that I am an ABR. He is also an ABR. I am an ABR. He is also an ABR. But only one of the ABRs can forward the LSA to the next area. Only one ABR can forward the LSA number 5 to the next area. That is the condition. And that is again based on the highest router ID. Whichever router has the highest router ID will forward the LSA number 5 to the next area. And in this case, it is R3. So LSA number, they both will decide. It's a mutual understanding between them. So when R4 forwards the LSA number 5 to R2, R2 is not going to forward it. It is R3 which will forward it to R1. R1 will forward it to R2. But R2 now has the LSA coming directly from R4, the other coming from R1. Again, what is going to happen? He will choose the shortest path to reach the ASBR. Why will he choose the longer path like this? So here again, the loop is avoided from a shorter path. This is an interview question. Which ABR will be chosen? Clear? Any question? Srinivas?
Yeah,
Hello?
I got it. Yes.
Okay. Okay, my bad. The default is 20 and the cost is E2. Okay. Now they may ask what's the difference between E1 and E2 routes? E1 and E2 routes in what do you say? OSPF. Simple. By default, when you redistribute, it chooses E2 and the cost is 20 by default. So what happens is that here, let's say it shows E2. So here, no matter how many routes or how many routers you have in between, for R4 to reach the external network, the cost is always 20. The cost is always 20. It is not considering its cost between R4 to R1 and R1 to R2. It is not at all considering that cost. It is considering that its cost to reach the EIGRP network is 20, completely ignoring the router costs in between. However, when we are redistributing, we can change this default behavior and convert it into E1. When we are converting it into E1, the cost is 20. However, now R4 will also consider its cost to reach R1 and R1 to R2 as well. So 20 plus 1 plus 1 equals 22. This is the E1 cost. But the default, that is E2, no matter how many routers are in between, the cost is always 20 to reach the external network. This is the difference between E1 and E2. Clear? Any question?
I don't know, but where we require this load balancing, like on this, when multiple links having same cost. In the last scenario, it is not required for load balancing. I think
This one.
Yes, not required. No?
It is not. It's not going to happen.
Yeah. Okay.
It is not going to happen. Load balancing is not going to happen because we have two ABRs connected to two same areas. In this scenario, load balancing will not happen.
Yeah,
okay. Where will load balancing happen? Did we check here? Yeah, load balancing will happen. Obviously, equal cost multipathing when you are getting the same destination, okay, from two different routers which are not ABRs, not connected to two same areas or like that. and have the same cost. Then only you will have equal cost multipath. Otherwise, it will not happen. So for every protocol says I will choose the best path, and my best path is only going to be one until and unless exclusively specified that I can do multipath. Clear?
Yeah, yes. I think only one route should ABR should be there. From there, I think multiple paths.
Correct.
Yes. Oh,
Correct.
got it. Yeah.